So I'm going to be talking to you today about some continuation of work that we did with some colleagues, Goddard, namely Juan Diego and Diego. Those are two different people in Menelaos. They calculated the updated impact flux or impact melt flux generated from micrometeor bombardments. And we used that to kind of simulate how much water was being generated from solar wind recombinant absorption processes and those impact melts. So this part is basically calculating the exospheric number densities for hydrogen and water from those processes. So just some background of the model. This is kind of a very simple cartoon schematic of the kinetic model that we developed to simulate this. So here we just have a metal oxide lattice that you would expect to see in a grain. It's just a generic one. The surface is designated as green. The subsurface implantation kind of radiation zone is this orange, and this bulk is designated as red. So we all know that hydrogen is implanted into the regolith that generates these hydroxyls. These hydroxyls can then diffuse to the surface or down into the bulk. In addition to that, we have oxygen ions from the solar wind. This as well will create these peroxide defects, which can then diffuse up to the bulk and up to the surface as well. So it's really a combination of hydrogen and oxygen implantation that will ultimately result in a grain that has these hydroxyl active sites on the surface as well as in the bulk. And so if you give some sort of energy to that system, either with solar photons to warm it up or through a micrometeor impact event, which we saw earlier, you will actually make some water, either gas phase or some trapped in the impact melts. I'm going to skip this slide to save some time. This is just an argument for why we don't really see mass transport into the bulk. Most of you have probably seen this slide by me or by Tom at earlier conferences here. This is just kind of an overview, a very simple introduction to what recombinant absorption is. It's basically a simultaneous reaction absorption event between those hydroxyls. This right here is just an example of SiO2. The figure here is just showing the decrease in that infrared OH stretching as a function of temperature. These authors identified two different sites, a geminal and vicinal site. So the geminal site actually occurs at a lower temperature just due to the proximity of those two reactive groups. However, if you also include other ions and actually create these minerals that are representative of actual lunar regolith, you can actually start to shift those activation energies and those onset temperatures down lower. So for example, titanium dioxide has a recombinant desorption onset temperature of about 250 Kelvin. So now we're really in the regime where it's relevant to the lunar J-site surface. However, all this is really, it doesn't matter, it's irrelevant when you have an impact event, right? An impact event is going to melt some of the grain or a whole of the grain. And that occurs at around 1600 Kelvin or so. And so that's plenty of energy to overcome any of these activation energies. And so there's going to definitely be water made as well as some hydrogen. Okay, so this is a kind of a culmination of those modeling efforts. This was recently published in a Planetary Science Journal. The top is the water production rates for recombinant absorption, and the bottom is production rates from impact melts. And this is just a different snapshot. So on the left is the early on, so after about 100 lunar days. In the middle is about 1,000 lunar days, and 10,000 lunar days is on the right. So recombinant absorption is a very thermal-driven process, right? So it's going to occur at the very hot part on the lunar surface, which is at the subsolar point along the warm equatorial regions. The impact melt will at first follow the deposition of the solar wind flux, but you can see this peak migration of water production towards the poles, and that's just due to the fact that the higher latitudes, due to the colder temperatures, will retain more of the hydrogen, which leads to higher production of water, and that's why you kind of see it migrating toward the pole there. Okay, so this is just a quick summary of the Exosphere model. This is very similar to what other people have done. Molecules were launched at thermalized velocities relative to the surface. Trajectories are calculated taking into account for the spin of the moon. I used Monte Carlo kinetic scheme to kind of choose the ultimate chemical fate of the molecule. This includes absorption, dissociative absorption, photodissociation, cold trapping in PSRs, and Jeans escape. And for the discussion here, I just kind of chose an arbitrary flight path from the subsolar equator point to a North Pole just to kind of estimate the particle number density for these molecules. I also just want to point out that these loss mechanisms are really negligible for hydrogen. The dominant one is Jeans escape, so that will come into effect later. So here is the exospheric number density that we would expect from water. This is later on, after about 10,000 lunar days of simulation. So you can see that the scale height is relatively high, about 100 kilometers or so, before the number density drops off really quickly. And like I said, this is a thermally different process. So the majority of the exospheric number densities are centered around that subsolar point in those warm equatorial regions as well. And this is just kind of a slice at 50 kilometers or so. I just chose this as it kind of mimics the lattice space height. And so you can see again, it's peaking at that subsolar point and decreases quite rapidly as you go towards the poles. One thing I also want to mention too, and this was brought up during Paul and Abigail's talk, is the fact that what you're seeing here is about a 5 to 10 ppm change, right? So the number density is already an order of magnitude of what is as measured. So where measured values kind of indicate it's about 1 to 5 molecules per cubic centimeter. And so you can see that if we really are seeing 100 ppm shift or on that order, the exospheric number density used to be quite high and quite easily measurable by spacecraft instruments. Okay, so hydrogen formation, this has always been in the model. We've never really talked about it in our papers, just because we've been more focused on kind of the infrared absorption bands that are happening on the lunar surface. But basically, the premise is really simple. So you form these hydroxyls, you keep pumping in hydrogen into the regolith. It needs to go somewhere. That will react with those hydroxyls to form trapped molecular hydrogen. That trapped molecular hydrogen can then diffuse through the surface and enter the exosphere. This kind of explains why we see blistering as well, because you have these hydrogen accumulating. So I took that kinetic model and I fit it to Michael Scheibel's data. So I'm sorry I forgot the reference, but he irradiated some olivine, measured the OH column density, saw an increase as a function of total fluence. And so that's what you see in the black squares there are his experimental results. The red line is a fit. The blue line is just a decrease in those what I call precursor sites, or generically the MOM sites. And so here is when you start to see the hydrogen production, right? Hydrogen production really is only going to start happening after you build up a reservoir of those hydroxyls to react with. And it becomes quite linear. So the more hydrogen you're putting in, the more molecular hydrogen is coming out. Okay, so this is kind of the simulated expected outgassing for molecular hydrogen. This is after about 10,000 lunar days again. You can see again, it's centered around the subsolar point in those warm equatorial regions. It's a thermally driven process. The magnitude is very similar to water as well.
You have 2 minutes.
About 10 to the 6, 10 to the 7 molecules per centimeter squared per second. This is the exospheric number density that you would expect to see early on in the simulation. So here the overall number densities are relatively low, just because the production of hydrogen is relatively low early on. Again, it's focused around that subsolar point in the warm equatorial regions. The scale height is quite high here. That's just due to the fact that hydrogen is a much lighter molecule, so it's getting up into the exosphere much easier. However, going back to what I mentioned, are the loss mechanisms. Not really a lot of loss mechanisms for hydrogen. So hydrogen will start to accumulate in the cold areas, and that's on the night side and in the poles, right? So this is just kind of a snapshot of where these molecules are being launched from after about 10,000 lunar days. So what this means then is that you start to actually see a concentration of hydrogen in the exosphere near those cold areas, near the poles. And then I'll just jump to comparison with some observations. So on the right is the CHASE neutron mass spectrometer. You can kind of see that it matches fairly well. We start to see this increase around 70 degrees north. The number densities also match about 800 molecules per centimeter cubed. And also we generally see hydrogen basically everywhere. It's just concentrated in those cold regions. One thing here is the scale height doesn't really match. They're seeing 800 molecules per centimeter cubed all the way up about 100 kilometers, and I don't really see that. One thing that could possibly explain that is that these impact events are causing the hydrogen to scatter up even higher into the exosphere. So just to summarize, hydrogen is being produced from solar wind. This happens after the regolith has kind of developed a reservoir of hydroxyls. This hydrogen can then diffuse through the grain. Initially, the hydrogen is localized in the warm equatorial regions. However, over time, it kind of accumulates in the cold parts of the lunar surface, which results into an increase in the number density near the polar regions. Water is a little different because it has lots of loss mechanisms. So the overall transport length is pretty short compared to hydrogen. And so you don't really get that buildup in the cold parts. With that, I'll just say that our funding agencies, thank you to them. And I'll end there. Thank you.
Thank you. No time for questions.
Okay, then our next speaker is Sean Gopalakrishnan, giving a talk about lava tubes.